Crochet and our team here. We're quite a small team of 4 hydrologists working with different kind of hydrological models. Vasim ETH is a more physically based one, and HBV, which we have been using, which I have been using at the University of Zurich. So the work I'm going to present is going to be first a little bit the things I've been doing in Switzerland during the last 5 years at the University of Zurich, ETH, and also together with the colleagues from the University of Graz, Andreas Gobier, with the group of Andreas Gobier climate change projections. So I hope to give you an insight of what we have been doing, and also would like to give you an outlook of what we would like to do, and maybe we can get into a discussion on our approaches and come up with a scientific dialogue between different groups. So I want to first start out. Let me see. Yes, I want to first start out with a general overview of hydropower in Europe. And we all know that in the European Alps, a lot of hydropower is going on. Austria and Switzerland, they depend very strongly on hydropower production, and in Northern Europe as well, Norway as well, a lot of hydropower production in Sweden as well. So I just put here some figures to see in what context we're doing this hydrological modeling. And in particular, I want to point out that in Iceland, hydropower production is a quite important factor. Actually, we produce more energy than is actually needed for the population, because we have these aluminium melters, which require a lot of energy. And if you look at these figures here, so the entire Europe produces about 400 terawatts per hour per year annually of hydropower energy. Norway produces about 120, Austria almost 40 terawatt hours, Switzerland 35, and Iceland, actually, given that we are only 320,000 people living on the island here, 12 terawatt hours, but the potential is actually estimated to be a lot higher, and I will get back to this huge number of 220 terawatt hours annually, which could be produced here in Iceland, which is estimated by our National Energy Authority on their webpage. So that's the setting. Given that Iceland is only about 530 kilometers away from the UK, we might consider this as well within our model. So coming back, most of the topics last 5 years I've been developing hydrological models in Switzerland. So you see here the biggest hydropower dam in Switzerland, Conceptual, with a very high, over 1,000 meter of altitude elevation, and on the right-hand side we see the biggest dam in Iceland. And here again some background figures on energy production in Switzerland. 40% come from nuclear power, more than 50% from hydropower, and here in Iceland almost 70% of the energy production comes from hydropower, and the rest is renewable. Geothermal energy is also a big import. So here, these two figures are also quite important, because we see here that peak production is actually a little bit lower than in Switzerland. Here, Rhoneglacier with almost 2,000 megawatt peak production, but annual production is about 2,000 gigawatt hours. Here in Iceland, with these dams, we are actually more producing energy continuously and throughout the year, but the annual production is quite high. So I will get back to this, because this is actually quite interesting if you compare this to the meteorological data later on in my talk. So of course, Switzerland in Central Europe is embedded actually in the energy market. They can trade off energy, and this is actually given with these figures from the Federal Office of Energy of Switzerland, which I've put together in a couple of years ago. And you see here the production and the consumption. Of course, in Switzerland we have more production than is actually used during summer months, and less production than is actually used during winter months. So there has to be a trade-off where energy is traded with the surrounding countries. And of course, this is quite relevant if you look at the water which will be available to actually produce energy, and here comes the entire motivation for our entire work, to see actually, to anticipate how water availability will change in the coming months for energy production. Especially this year, 2014 was a very snowfall poor year. We had a little snowfall, very nice February here in Iceland, and this actually led to quite some concerns of if we will actually be able to provide and fulfill the energy requirements for all the aluminium melters. This has been discussed in the newspapers. So one of our objectives is, of course, to try to make some forecasts, not forecasts or predictions, how the seasonal snowpack and the seasonal glacial melt contribution will evolve during the coming months. So that's our objective and the motivation behind it. And of course, if you look at longer time, if you look at a couple of years ahead, then of course there's this underwater cable which has been discussed also in the newspapers recently, which could be built between Iceland and the UK, and then an energy trade-off would be possible between Europe and Iceland. So coming back now, focusing on hydrology and what we're actually interested in, because we're at the Icelandic Met Office, we're mainly looking at trying to use hydrological models, combine them with weather forecasts, and then kind of estimate how the water availability will be. So you have here discharge. Usually you have a groundwater contribution to a discharge, and then you have a glacier contribution, which comes in most cases at the second half of the summer. And then you have the snowmelt contribution, which comes in spring as soon as it gets warmer and days get longer. And the rest of discharge comes from local precipitation, so it's very difficult to estimate what the actual discharge is because it depends on direct precipitation. So this is a little bit what we try to do, to kind of estimate the contributions from different sources to the total discharge finally available in a catchment. So if you look at the hydrological model, this is the very simplest one. Our friend John has a stone where he just looks out toward the window and looks at the stone and then makes an observation, then he interprets the observation and finally comes up with a statement how the weather is going to be. Of course, this is very simple, but it's also only instantaneous. And if you want to look a couple of days ahead or a couple of weeks ahead, then it might be wise to use a hydrological model to kind of use either physically based or empirical relations to make an estimate into the future. So, and if you look at the simplest models, outgoing from the simplest model, the stone of our friend John, then you can go in three directions. You can go from conceptual to physically based models. You can go from event-based to continuous simulations. So this has also been discussed recently, that with climate change, parameters of hydrological models might change as well. So of course, but if you want to do a prediction into the future, we need a model which can run with the same parameters also for different climate settings. And then you have the third dimension, going from lump to distributed model. So here it depends on your research question again. If you have a very complex catchment where you want to deviate water and you are actually looking at the geographic and topography where all those kind of aspects are important, then you might consider to use a distributed model. Otherwise, you might be also quite well off with a lumped model. So in exactly this topic, we have been investigating last year together in the group with Jan Seibert at the University of Zurich, and we have actually been looking at three different model complexities using the HBV model, which has been developed in Sweden, and Jan has been working a lot with it. So we used three complexities. First, we used the very simple HBV model, then we used a little bit more complex one with three exposition zones. accounting for north and south facing slopes and east-west facing slopes. And then a more complex model with 3 vegetation zones accounting for swamps, forests, and grassland. And finally, we compared it to a physically based, fully distributed model like Topkapi or Vasim ETH, both currently being developed at ETH. Vasim also, both have been developed at ETH. Topkapi has originally been developed at Polimilano by Torini. So we then compared how these 3 models or these different model complexities perform if we use only discharge data, if we use also Monte's snow cover data, additionally to get an information about where is snow and where is no snow. And finally, we compared it if we also have glacier mass balances and if the performance of the model becomes higher. So this has actually also been discussed quite nicely by Grayson, but we try to quantify this discussion between data availability and model complexity within this study we've been performing last year. So I want to present some results of 4 case studies in Switzerland, and the Rhoneglacier, Hinterrhein. The Rhoneglacier is a small glacier, about 30 of a catchment, about 40 square kilometers, pretty much in the center of Switzerland. Hinterrhein is the source of the Rhine River. It's a little bit larger, this catchment, and finally Landquart with the Silvretta Glacier between just adjacent to Austria at the border of Switzerland and Austria. And finally, I want to talk also a little bit about the study on the Vispervalley, where we have this hydropower dam with the Rhoneglacier just next to the catchment and the Matmach reservoir inside the catchment. So, these are the 3 observational data sets we use to calibrate out on our model. We have discharge data with hourly resolution. They're originally recorded in 10-minute resolution, but for the study we used it then for hourly, and actually for the HBV model then we use daily discharge data. Glacier mass balances, they are available seasonally, so in spring and in fall, twice a year. People from ETH go out there and measure the change of volume of the glacier. So these observations are mainly performed by VAW, the group of Martin Funk at ETH, and finally these Monte's data, which are available freely on the internet and which can be downloaded for almost every area in the world. So we have tested these Monte's data. We are currently testing them for Iceland right here. It seems to work also for the northern countries. So that's why we are very confident to use this method also in Iceland. So the way we calibrate it is in principle a Monte Carlo simulation. This has been in detail described in our paper from 2011. We set up our model. We generate 10,000 random parameter sets. We let it run. Then we rank the parameter sets according to the 3 criteria. So here it's simplified in the paper. We actually use 6 criteria, 2 for discharge, logarithmic Nash Sutcliffe and Nash Sutcliffe, 2 for the glacier mass balances. So in principle, it's just a root mean square error between the observation and the simulations. And finally, a correctly predicted snow cover index, where it's in principle just an index of correctly predicted snow cover area divided by the total available observational area for snow cover. Of course, if the area is covered by clouds, then the satellite doesn't see anything, so we have to account this by this C missing. So what we do when we have these 10,000 runs, we rank them. We determine an overall performance, which is in principle nothing else than the average of this ranking value, which is described by, which is in principle just a rank of when you rank the 10,000 runs according to the efficiency of the different criteria. So So what we can do then, we can select out of the 10,000 runs the best runs regarding discharge. So in this case, it's in the Nash-Sutcliffe coefficient. Regarding snow cover, then we use this correctly predicted snow cover index. Regarding glacial mass balances, then it's the Vroom's mean error. And then we can select them regarding discharge and snow cover, regarding discharge and glacial mass balances, regarding mass balances and snow cover, and finally, regarding all three data sets. So we did this for these 4 different model complexities. The HBV1 model, which has only altitude bands. You see it here in the left image. So it only has altitude bands and doesn't account for south or north facing slopes or east and west facing slopes. Then the second HBV model, and there we have this specification. So we have south facing slopes, east west facing slopes, and north facing slopes. And finally, in the HBV3 model, we also have different vegetation zones, like swamp, a grassland, and rocks. And then we compared it to the Topkapi model, which is fully distributed, physically based, and has a grid size of 250 meter resolution. So here you have a little bit of the background of those 3 models we used. Those are the 3 catchments we investigated again. Rhoneglacier is really here in the central Switzerland, Hinterrhein, a little bit to the east, and then Landquart, all the way at the border to Austria, between Austria and Switzerland. And so here are the results, and actually that's the interesting, that here it becomes quite interesting. So you see here the discharge, the hydrographs, you see the range of the 100 best runs within the 10,000 Monte Carlo simulations we made. So you see that this corresponds quite well. You have some days where it's a little bit off. and you see here the ratio of snow cover. Again, the gray band is what comes out of the 100 best Monte Carlo runs. And in blue, you see actually what is predicted by the satellite, not predicted, but observed by satellite images. And you see actually that the gray and the blue correspond quite adequately, one would say. And the same thing here, the glacier mass balances, again, the observations or the reference mass balance based on the work of Matthias Huss from when he was doing his work at the Vispervalley at ETH Zurich. So we see here that our modeled glacier mass balances correspond quite well to the observed ones. If we were to use only discharge, then you see here the best simulations regarding discharge is slightly better than the gray zone, which has a bigger uncertainty. But you see also that if we use only discharge to select the best run, then here in the glacier, in the snow cover, in the predicted snow cover, we completely overestimate snow cover during summertime. Because we don't have anything to constrain the models to correctly predict the snow cover area. The same thing can be observed in the glacier mass balances. If we don't use the glacier mass balances or the snow cover, and we just use discharge to calibrate our model, then our glacier mass balance is completely off, as you can see here, with these gray lines given in this figure, subfigure D, subplot D. So I wanted to make our connections now with the hydropower companies who actually want to know how much water will be available in the coming months. And if you look at this, of course, we can calibrate our model. So the 3 different model complexities here in plot A, they don't show a significant difference. You see here, these are the mean discharge rates simulated by the model. And you see here that the 3 different HBV1, 2, and 3, they come up actually with the same monthly discharge rates. They also come up with the same monthly glacial melt rates, and also with the same monthly infiltration into the soil of rainfall. So we cannot really distinguish any difference between the 3 complexities of the HBV model. However, we see a big difference in, if you look at the snow cover ratio, if we use the HBV3 model and we calibrate it only with discharge, then we see here, this is the white bar. The white bar completely overestimates the snow cover during the melting season, as you can see here by this white bar. The blue line indicates what's observed in satellite images. And if you compare this to a calibration with discharge and snow cover, then you can see that we're here significantly more realistic in the contribution of snow, in estimating the snow cover, and finally also estimating the contribution of snow melt to the discharge. And this, of course, then is reflected by the glacial outflow. We see here that the glacial outflow, if it's calibrated only with discharge data, is underestimated, while if we calibrate our model with satellite images and discharge data, then we are probably at a more realistic rate. Same thing can be observed here for the rain infiltration. We see here that we actually underestimate the rain infiltration if we use only discharge data to calibrate our model. So this leads us to our overall consistency performance. So if we use all three data sets, so this is a comparison of the four model complexities versus different data sets used to calibrate our model. And on the y-axis, we have the overall consistency performance, which is in principle, it's just the mean ranking value of the 10,000 runs if we select only with discharge, if we select only with snow cover data, or if we select with mass balances or combinations of two or three observational data sets. By definition, we get the highest overall consistency if we use all three data sets, as is here visualized with the bars all the way on the right, where we have discharge, snow cover, mass balances. If we use only discharge, then the overall consistency performance is is a lot lower, because we get the mass balances and snow cover wrong. If we use snow cover, then it's even lower than using discharge, because then we only know where is snow and where not. We have no information about the volume of the water generated. And mass balances, there we have a slight combination. But what's quite surprising is actually that if we use discharge data and snow cover images, then the performance is actually closest to as if we were to use all three data sets. We have discussed this also in our paper in 2011, and we actually argue that this is mainly due to because satellite images have the aerial information, while discharge data have the volume information, and the combination of those two informations are best suitable to calibrate our hydrological model. So this is the final result we want to come up, and we actually want to provide afterwards to hydropower companies, estimations of total discharge, of rainfall, of snow melt, and of ice for the three different catchments. And of course, we then looked at different years, so we validated our results because we used only 1 year for calibration purposes. So we validated our years afterwards for a longer time period to make sure that this is also valid for different climatic settings, like for example in 2003 when we had an extreme heat wave hitting Europe, or 2005 with the extreme floodings. And finally, we also compared the three catchments. And here, actually, that's quite interesting, is that, here you see again the mass subject, snow cover images, and mass balances. But what's very interesting is actually that the overall consistency performance, if you go from a catchment which is very glaciated, so Rhone catchment has 52% glaciation, Hinterrhein has 17% glaciation, Longport has only 8%, then the importance of snow cover images becomes more and more, higher and higher. Of course, if you have a high glacial contribution, then the mass balances are most important to use for calibration purposes. So this reflects just that you have to see your catchment. If you have a catchment with a high glacial contribution, then it would be very wise to use mass balances for calibration purposes. Okay, so I want to come to my next case study, which is climate change projections. And actually I have to speed a little bit up, so I want to shorten this a little bit. So this is a study we've done in 2012. We used exactly the same calibration. So this is the Stausee, where you have a lot of deviations of rivers. So for this purpose, you need a physically distributed and spatially distributed model, because you need to actually deviate the water into the reservoirs. So here it is quite important that we use a spatially distributed model for our purposes. And you see here the discharge, which has been changing due to the construction of the river. So I want to actually come to this figure here, because here this shows very nicely that over 8 years, the discharge has, using our calibration technique, the discharge has been calibrated quite nice, but also the snow cover stays more or less constant over the year, and it doesn't pile up snow, which has been usually which is frequently a concern of hydrological modelers if they run a hydrological model over longer time periods, that snow piles up in the upper parts of the catchment in the model. But if we use these glacial mass balances, we can actually show that this doesn't diverge. If we use these snow cover images then we can actually show that this doesn't diverge, and actually is also over longer time periods consistent. So yeah, I want to these are these quantile mapping approach which you use to make climate change projections. So what we want to get there, we want to get the mean and the variability more or less correct for the present time period in order to make a projection into the future. And once we have, so we use 30 years to do our quantile mapping for the present period, and then made projections into the future to estimate how climate change will impact hydropower production. And here also, okay, yeah, how are we doing in time? I might have to shorten this a little bit.
Yeah, well, we have, you can go on for a while, 10 minutes maybe.
Okay, then I'll go on for about 10 minutes, okay. So, in principle, these projections, what I want to get at is that we use 10 parameter sets to calibrate within our 10,000 runs of Monte Carlo simulations. We use 3 glacial retreat scenarios to estimate the error in glacial retreat, and we also used 7 climate change scenarios to make a projections into the future, totaling into 210 simulations in total. And then we could actually make a projections into the future. And what's important here, that when we look at these mean projections we made into the future, you see these differences, that the ice melt will of course decrease. The lake level of the hydropower company will decrease as well. And we actually compared the uncertainty of our projections into the future with what we expect to be the change. And actually that's a quite important point, because when you want to do projections into the future, you want to account for the uncertainty, but you want to also show what part of the modeling is actually predicts such a big change that it is bigger than the expected uncertainty. And this is actually what we show here. So you have here the mean projection for the future, and then the standard deviation of the mean. And if the standard deviation of the mean is smaller than the expected change due to climate change into the future, then we argue that our predicted changes are significant and that they can be actually that this could be realistic. So using ANOVA, we can also assess where the uncertainty comes from. So all this has been explained in detail in our paper in 2012. So if you have a question, we can discuss it maybe later. But what seems to be important is also these climate extremes. If you look at the discharge today, so this is the excess water. If you have extreme melting periods during the summer months, then the water intakes for hydropower companies are sometimes constructed too small, so the water overflows and the intakes are too small to take in all the water. And if you look at our projections, then we can actually see that most of this water today is due to intense glacial melt, while in the future it will be due to intense precipitation events. So those were actually the conclusions of our climate change projections in the paper we published in 2012. So that's why I actually jumped a little bit over the last few slides, because I want to actually state what we want to do here at the Icelandic Met Office and what we've been discussing with Philip Crochet and within our team of hydrologists here at the Met Office. And what we are actually interested in now is to use hydrological models and to come up with short-term, medium-term, and seasonal projections of how groundwater, ice melt, snow melt, and total discharge is going to evolve in the future. So yeah, and of course we want to account for the uncertainty again by using Monte Carlo simulations, so that we can a little bit assess what is the uncertainty of these three contributions to discharge in different catchments. So the interesting thing about Iceland, that we have already gridded input data, and this is the work of Philip in 2007. And what you see here is actually that the precipitation is extreme. You have over 7,000 millimeters of precipitation in some parts of the area. So this is the mean annual precipitation between 1970 and 2000, and this figure actually depicts very well how extreme the weather can be, with extreme precipitations in one part of the country, in other parts a little bit less. And also mean January temperature, you see here, so if you think about it, that these are mean January temperatures over the 30 years, and you have here minus 12 degrees on top of the biggest glacier, Rhoneglacier. And you have at other areas of the country 12 degrees mean average temperature. So you have a quite extreme weather conditions here in Iceland as well. But so we have this gridded data, and what we want to do is now to use either the weather forecast from the European Center for Medium Range Weather Forecasts, and then make statistical corrections to use our hydrological models to predict the contribution of discharge, snow melt, ice melt, and rain, and of course also to estimate the snow water equivalents. So there are three different kind of forecasts we're looking at. Short term, this would be more like for flood forecast, 48 hours ahead. Medium term, 3 to 10 days, and seasonal up to 7 months. And then a typical expected output would be a figure like this, which we could provide to stakeholders to tell them, for example, how the seasonal evolution would be. And this is really work we're working on right now, and we're actually looking into how this could be done. So Philip has already been working on a precipitation map, predicting forecasting the precipitation using the ECMWF forecast, and then statistically correcting them to come up with a 1 kilometer resolution, so that we have a data set for the forecast which is consistent with the data sets we use to calibrate and drive our models for calibration purposes. And so that's a little bit what we want to go into. And of course, we are actually, we are looking for partners to team up and to start scientific discussions on these topics. Since we're quite a small team, but we are, so these are the kind of things we want to do in the coming years. So I come to the conclusion of my talk. We are convinced that multi-variable calibration increases overall performance, especially discharge data and snow cover images, can constrain hydrological models in a very good way so that we can make predictions more realistic. Based on our analysis, model complexity does not really increase performance if you look just at the total discharge of the catchment, but of course if you have a specific questions where you need to account for deviations of rivers and where the topography of the catchment becomes very important, then it might be useful to use a distributed model. So we're looking at both kind of types of models, like conceptual models, lumped models, and also distributed and physically based models. And yeah, the value of snow cover images, of course, it increases with decreasing glaciations, because if you have big catchments with a very small glaciation component, then of course the component of the glacier is a lot lower, so then the snow cover images become even more important. And so up to now, this method we have been developing for Switzerland is working quite well in Iceland, so we are convinced that this could be applied also to other catchments. So finally, yeah, we're still looking to join in or to team up with the scientific community on different scientific calls. So if you are interested in joining or having us as a partner in Horizon 2020, then we would be very happy to discuss this. And with this, I would like to thank all the co-authors and all the staff and colleagues and friends from Switzerland and from Austria as well, with whom I've been working during the last 5 years, especially from the Paulo Borlando's group at ETH, Andreas Goviet's group in Graz, and Jan Seibert's group at University of Zurich. So yeah, I'm open for questions.
Okay, thank you very much, David, for a very interesting talk, and it's very nice to see the how you use the different data to do calibration as well. So I will just open the floor now to any questions. So if you want to have a question, please unmute yourself on the red button and go ahead.
Hey, David, this is James McCrite. I'm at NCAR in Boulder, Colorado, and I guess my first question is, where is this picture? Really an excellent picture.
Oh, yeah, the picture. Yeah, this is the picture. It's close to the Vatnajökull on the west side of Vatnajökull. Actually, this water flows afterwards into one of the hydropower dams. I haven't been there myself yet, but I intend to go there this summer. And it just shows the beauty of Iceland. It's really a magnificent country.
Certainly, yeah. So I was just, my main scientific question on your presentation is, in the first part of your presentation, I didn't understand if all the results you were showing, all the verification statistics were basically in simulation mode, or if some of those were in forecast mode. I don't know why I didn't.
Yes, because those were not yet they were not yet forecast, so okay. We haven't done forecast yet. So up to now, we have been only working on well, the only thing what we did was climate change projections. Okay. And there we could not verify it, but the entire forecasting is actually what we intend to do in the next coming months, and to use the advances we have been doing in hydrological modeling and to apply it to forecast using satellite images and discharge, and glacier mass balances to improve forecasts. But we have not yet tested the hydrological models to do actual forecasting.
Right. And so what time scale is the hydropower? What is their primary forecast window of interest? Do they want like 48-hour, or are they interested in a variety of forecast windows?
Well, there are actually two forecasts they're interested in. One is, of course, seasonal, because if we know how much, if we have a certain situation after winter and we have a certain snowpack, then it would be interesting to know how much water will be available in the coming months, and will they be able to fulfill the energy production that they promised. And of course, short term is also important, but I would guess that this is more. Yeah, we would have to discuss this with the hydropower companies, but this is probably more impacting on the price evolution of the energy.
Okay. And do you have any plans to do any sort of data simulation in forecast mode?
Yes, so that's what we've been discussing with Philip. Maybe Philip will give a presentation more in detail on the forecasting in the coming months. But that's what we are planning to do, actually, to see how well the analog forecasting of Philip, or the statistical downscaling of numerical forecasts, how well this can be applied to a hydrological model, and how well then this and to kind of verify and validate our forecasting with a hydrological model.
Okay, great. Well, I look forward to your results. Thank you.
Okay, thank you.
Okay, there might be more questions. Elias, do you want to have a question?
Yes. Good evening, everybody. That's Elias from HEPEX. Thank you very much, David, for this.
Okay, thank you.
Really interesting presentation. Thank you.
Yes.
I do have two questions, more into the modeling part of the work, because we are also going to do something similar at SMHI with the HYPE model, the European version, combining satellite information. So actually, my first question is, if you have noticed any changes or any biases when you calibrate the model using the three different objectives that you have, coming from the three different data sources. So if the parameters, let's say the behavioral parameters, the range of those change when you compare those three different objectives. So that's the first question. And then the second question is, I'm actually a bit surprised, because I would expect that the satellite data have, apart from information, they have quite a lot of error as well in their actual value. So I was actually wondering if you have considered this uncertainty in the raw values when you do this calibration of the parameters. Yes, thank you.
Yeah, I didn't quite understand your first question, because acoustically was.
Yes, yeah. It's actually simple. You calibrate the model using discharge data, so against discharge data, and then you have these 100 best sets of those. And
yes.
Then you calibrate again the model, introducing, apart from discharge, but another objective, which could be the snow cover or the water or the mass balance.
Yes.
So I was wondering if the 100 parameter sets change when you when you go to different objectives.
Yes, yes. So we discussed this a little bit in our paper also. Let me quickly. Oh, I have to take this away. So it's in principle of course we get different parameter sets if we select only according to discharge, or only according to snow cover, or only according to mass balances. If we could actually show also that if we combine the data sets, some of the parameters get better constrained within the 100 best runs than if we don't combine two data sets to calibrate, to select the best runs. So, so this is to your first question, and to your second question on the errors in the observational data sets. So, of course, it's true that you would probably also have an error in the discharge data, because this is just a rating curve, and especially if you have high discharges, you probably have also an error in the observation, which you should account for. And it's true that also here in the snow cover, in fact, there are quite some periods which are covered by cloud, and there we just linearly interpolate. And there's of course also an uncertainty within the actual image, and probably not all the pixels can be considered to be correctly predicted, but it's not. This was not our objective to verify the Moody's data. There's a lot of literature on the occurrency of the Moody's data, and since we're looking at reasonably large catchments, some of them are over 100 square kilometers large, we're not so much interested in an error of one individual pixel of the Moody's image, but rather to get the general snow cover within a catchment. And I believe that this is actually quite accurately predicted by Moody's. There might be an error of, I don't know, I would estimate a couple of %, but as the blue line here shows, it seems to be quite realistic, and it has been verified with webcams and other data sets, but it was not the objective of our study. And the glacial mass balances, of course, glacial mass balances have also an uncertainty within it, and we might consider it as well in the simulations. But and in fact, we only used a glacial mass balance, a reference glacial mass balance, coming out of another model from Matthias Huss's work, which has been calibrated with observed data. So yes, it's true that we should account for errors in the observational data as well, but it might, yeah, it has actually been discussed in other studies, and we refer to those studies in the paper. Does this answer your question?
Sorry, it was muted for a bit time, but yes, it does. I'm very satisfied with the answer. Thank you very much.
Okay, thank you.
Sorry, Elias, I muted you because you had an echo on your voice there, but you had the answer anyway. Okay, a final question before we round off here. You talked about using forecast data and calibrating the forecast data, or correcting the forecast data. What do you plan to use for that correction? Can you say anything about that? Because I mean, there's available the hindcast data, but that's only a limited number of ensembles, and the other option would possibly use the previous forecast to do this correction. Because we are thinking about the same lines here as well, so I was wondering if you have any comment on that.
So for the forecasting, we have in-house this harmony model, which is being used by our forecasters to make the forecast. And of course, this would be, but the harmony model, it runs on 2.5 kilometer spatial resolution. So then we would need to make a statistical correction to get it into a format that it corresponds to the model to the data we use to calibrate our hydrological model. So, and this is really work Philip Crochet has been working on, and actually I would like to refer to his work or to the talk he might give in a couple of weeks on this. But in principle, what it is for the short-term forecasts, we intend to use our in-house harmony model or the analog-based forecast of the numerical model from the European Center of Medium-Range Weather Forecasts, and then apply them, once we get them statistically corrected, to the gridded data we use to drive our hydrological models, then to come up with a discharge projections of up to 48 hours. For the medium term, 3 to 10 days for predictions, we intend to use either the ECM WF data and statistically correct them, or analog based on ECWMF forecasts to drive our model.
Yes, can I just comment on that? Because one problem, not the problem, but using the ECMWF model is that there's constant model upgrades. So the difficulty is to get a large enough data set to use in your statistical correction. So I was wondering if you had any ideas about how to get around that problem. Do you understand what I mean?
Yeah.
What I mean is that you don't have a long data series of models of the same, even the same resolution or the same statistical characteristics. So the model will change over time.
Yes.
But you don't have a data set which is statistically the same over a long time period.
Yes, I understand that probably in principle I would have to discuss this with Philip. Unfortunately, he's not here today because we have a public holiday today. But the way I see it is, in principle, it's the same discussion we had for the climate change projection when we used the Quantile mapping correction to correct the climate change projections, and we said that this correction is going to hold also in the future. And of course, the model will always change, but we have to somehow correct the data, and we have to assume some corrections which are also valid in the future, because otherwise it's not possible. Even if the model changes all the time, this is just one of the uncertainties we have to deal with. And of course, we intend to assess the uncertainty of our projections by testing the forecasting in the past.
Okay. Yeah, I'm looking forward to the next talk that we'll have in the next month. Okay. Thank you very much, David, and thank you, everybody.
Yes, thank you very much. I'm sorry it was difficult for me to hear all the questions, but acoustically. But it was great to have this experience. And thank you very much.
Okay. Thank you all.
Thank you.